For a modern enterprise, data is the primary asset. A bank that loses its account records, or a social network that loses its user connections, loses nearly all of its institutional value. When junior engineers first learn to build applications, they often treat data persistence as a straightforward file input-output problem. They write code asking the operating system to read and write data directly to standard files. On a small scale, this works. Imagine a hypothetical university storing its records. The computer science department creates an operating system file for its students, and music creates another. As the university scales, this approach breaks down. A student double majoring in computer science and music now has their address stored in two different files. If that address changes in one file but not the other, the data becomes inconsistent. This creates a data isolation problem. Because information is scattered across different files in varying formats, writing a new program to retrieve a specific list, like every student in one postal code, becomes difficult and inefficient. A database management system, or DBMS, is the engineering solution designed to manage these large collections of data, resolving the redundancies of standard file systems. The core responsibility of any modern DBMS is to store and retrieve interrelated data with extreme efficiency and absolute safety. To organize this complexity, the industry standard is the relational model. This model structures data into a collection of tables, establishing strict mathematical relations between different entities. Here, we see how relational tables operate. We have a table showing instructor data, including ID, name, and salary. Notice how the department name column logically connects each instructor to a separate department table that tracks building locations and budgets. While these structures appear clean and simple to the user, managing their underlying physical bytes across terabytes of disk space requires immense computational overhead. Before modern high-density storage, managing structured electronic records required the physical manipulation of massive tape drives, an environment where manual processing and early automation intersected. To understand a modern DBMS, we have to first look at exactly how a standard file system fails during critical operations, and then deconstruct the three-tier abstraction architecture required to fix it. One of the most significant flaws of a standard file system is its inability to survive a mid-operation hardware crash. Consider a standard banking transaction, transferring $500 from account A to account B. The system executes this transaction chronologically. First, the program reads account A and debits $500. Next, it must read account B to credit that same $500. Suppose a sudden power failure or system crash occurs exactly in the milliseconds after account A is debited, but before account B is credited. The $500 is permanently deleted from the system state. The file processing system has no built-in mechanism to remember partial transactions, leaving the database entirely inconsistent. This introduces an engineering requirement called atomicity. Atomicity is an architectural guarantee dictating that a complex set of operations executes completely in its entirety, or not at all. Without a dedicated engine designed to manage these complex all-or-nothing transactions, data integrity is left entirely at the mercy of hardware stability. The second flaw emerges from concurrency. When thousands of users interact with the exact same data simultaneously, anomalous behavior is inevitable. We can see this in a university registration stress test. Imagine a course is nearing its enrollment limit, and two students attempt to register for the very last seat at the exact same millisecond. Two separate background processes fire simultaneously. Both read the current enrollment count as 39, completely unaware of the other's intent. Both programs locally add 1 to the value they read, and both write back the number 40 to the database. Two students successfully registered, but the count only increased by 1 instead of reaching 41. Because the count registered as 40, both students bypass the enrollment limit. This concurrent write error directly violates the database's internal integrity constraints. Executing concurrent writes without a specialized overarching system supervisor will corrupt the state of an application. The DBMS addresses file complexity through an engineering paradigm of architectural decoupling. This vertical diagram illustrates the 3 levels of data abstraction used to hide low-level hardware interactions from the end user. At the bottom is the physical level. This layer describes the complex low-level data structures, disk blocks, and indices that dictate how the data is stored on the actual hardware. Above that sits the logical level. This contains the schema, which describes what data is being stored and maps the relationships between different records, like our instructor and department tables. Finally, the highest layer is the view level. This provides specialized subsets of the database tailored to specific users. A university registrar, for example, interacts with a view that shows student schedules, but hides instructor salary data. This hierarchy enables physical data independence. Engineers can reorganize the physical storage arrays on the bottom layer without breaking the application code running at the logical level above. By separating these layers, a database can handle multi-petabyte datasets and hardware upgrades while keeping the application's logic consistent and accessible. This flowchart maps the internal architecture of the DBMS engine, showing how declarative requests are processed. When a user submits an SQL query, it first enters the query processor, where the data manipulation language compiler translates the high-level request into machine-readable instructions. Because there are multiple ways to retrieve the same data, the query passes to the query optimizer. This component calculates statistics and selects the lowest cost evaluation plan from a set of mathematical alternatives. That optimal plan is then handed to the query evaluation engine, which executes the specific physical instructions required to fetch the data. The query processor functions as a translator, converting high-level requests into optimized physical operations. The evaluation engine then routes its instructions down into the storage manager, the component responsible for the interface with the physical hardware. Here, the buffer manager plays a crucial role. Since disk reads are slow, it fetches requested data from the hard drives and caches it in fast main memory to prevent bottlenecks. To ensure that mid-operation crashes don't wipe out a funds transfer, the transaction manager enforces atomicity and durability, logging actions so the system can recover to a consistent state. And to prevent the race conditions we saw during course registration, the concurrency control manager actively supervises simultaneous transactions, locking records to maintain data integrity. This deep engine architecture is what allows a DBMS to abstract away the physical realities of hardware limitations and concurrent access.